So this lecture, so over chapter 5, second lecture, we'll cover this concept of absolute stereochemistry. So if we take these two molecules, for example, and we name them, so 1, 2, 3, 4. So they are both 1, 2, 3, 4. So they are both 2-chlorobutane, but obviously they are different molecules because they're stereoisomers of each other. So we need a name. So we need a method to distinguish between them if we name these two molecules, for example, so that you would know which one you're working with. So we looked at in the last lecture these terms dl plus a minus, but that doesn't tell you the spatial arrangement of atoms in space. All that tells you, does it rotate plane polarized like clockwise or counterclockwise? So if we want to, we need a system that will describe the three-dimensional arrangement of atoms in space. And so you use the IUPAC. The way to do this is use the International Union of Pure and Applied Chemistry rules. So the Ingold prelog system, which will allow you to determine if the chiral center is R or S. So it's a pretty simple method to use. You use what are called sequence rules to establish what's called the absolute configuration. So if we have a chiral carbon, basically we're going to assign each of these a number 1 through 4 based on molar mass. Okay, so we're going to assign priorities based on atomic mass and rank the substituents 1 through 4 on the chiral carbon. So if we had a chiral carbon, it doesn't have to be carbonous, we'll see it can be other elements as well. Nitrogen can be chiral, sulfur can be chiral. So if two atoms are the same, then you go to the next atom in the sequence, and the next atom in the sequence until you find a point of difference. The first time at the first point of difference you find, you stop, and you assign your numbers 1 through 4. So if you run into multiple bonds in the sequence, then you're going to expand them out. So if we had a carbon-carbon double bond, for example, you would expand it out to two single bonds. So the same is true for oxygen, since it's double bonded to carbon. So there's one bond to carbon and there's another bond to carbon. So any double bond you expand out to 2 single bonds. And then, so it'll make more sense as we do this. So then we're going to orientate the molecule so that number 4 points away from us. So if the white was number 4, for example, I would want to view the molecule like that. So number 4 is pointing away from me. Or like that, so number 4 is pointing away from you. And then you're going to do like 1, 2, 3. And so from your perspective, that would be 1, 2, 3 counterclockwise. Right, so 1, 2, 3 would be counterclockwise. Okay, so if your arrow from 1 to 2 to 3 is clockwise, that's called the R isomer. If your arrow from 1 to 2 to 3 is counterclockwise, that's called the S isomer. So I'll show you a method where you don't actually have to orientate number 4 so that it points away from you. That's just an extra, that's the formal way to do it, basically using these rules, but there's an easier way to figure out R and S. So it'll make total sense as we do this few examples. So if we take these molecules, so that's your chiral carbon. So we're going to assign numbers 1 through 4 to everything attached to carbon based on molar mass. So if you look at a periodic table, chlorine's got a higher mass than hydrogen or carbon. And then hydrogen's got the smallest mass, so it's going to be number 4, and chlorine's going to be number 1. And then going this way, you run into a carbon, and going that way, you run into a carbon. So this is where the second rule applied. If two atoms are the same, go to the next atom. So this carbon then goes to a hydrogen, and a hydrogen, and a hydrogen. And this carbon goes to a hydrogen, and a carbon. So the carbon on the right goes to H, H, and C, and the carbon on the left goes to H, H, and H. And so this would beat that. So this is going to be going this way is number 2, and going this way is number 3. So then we're going to draw our arrow from 1 to 2 to 3, and that is clockwise, so that would be R. So this would be R2-chlorobutane. Okay, so if we did the same thing here, chlorine is priority number 1, that's priority number 2, and going to the left is priority number 3, and number 4 is hydrogen. So if we did our arrow from 1 to 2 to 3, that would be R, but then you have to apply these rules. So if number 4 is on a dashed wedge, like it is there, then you assign 1, 2, 3, and 4, and that's your answer. Whatever your arrow is, that's your answer. If it's clockwise, it's R. If it's counterclockwise, it's S. But if number 4 is on a solid wedge, like it is here, right, that's a solid wedge, then you draw your arrow from 1 to 2 to 3, like I just did. 1 to 2 to 3 would be R, but then you reverse it. So that's your final answer then. So 4 is on a solid wedge, draw your arrow from 1 to 2 to 3, and then change its direction, and that's your answer. So this would be the S isomer, so this would be S2 butanol. Okay, so let's see. So let's try this. So let's try these two. So they both have a chiral carbon right there. So see if you can figure out if they're R or S. So if you want to pause the video for a minute and assign stereochemistry, and then I'll do it for you, and you can see if you got the right answer or not. Okay, so let's assign priorities. So this carbon has got a hydrogen attached, it's got an oxygen attached. Going this way, it's got a carbon, and going that way, it's got a carbon. So we have hydrogen, oxygen, carbon, carbon to compare. So oxygen's got the highest mass, so it's 1. Hydrogen's got the smallest mass, so it's 4. And then the other two ways, so you might say, oh, okay, there's a bromine there. Bromine's got a higher mass than oxygen, but it doesn't matter because you go in order. You go oxygen, hydrogen, carbon, carbon. So you follow the sequence in order. And so oxygen beats carbon, so the bromine doesn't matter in that context. Okay, so now if we keep following the sequence to what is number 2 and what is number 3, so now we have to go to the next position. So this goes to H, H, and H, so H, H, and H. And this carbon goes to hydrogen, hydrogen, and that carbon, so H, H, C. So that wins, right? That beats that. The other two cancel each other out. So this way to the left is going to be 2, and the way to the right is going to be number 3. And then if you draw your arrow from 1 to 2 to 3, 1 to 2 to 3, that is counterclockwise, so this is S. So that stereochemistry of that chiral carbon is S. We can't name the molecule yet because we haven't looked at how to name alcohols, but at some point we will. So at this point, I wouldn't expect you to know how to name that molecule, but I would expect you to be able to determine if it's R or S. Okay, so for this next molecule, so the chiral carbon has a fluorine, and then 3 carbons attached, but then of course you would consider the entire sequence, but fluorine versus carbon, fluorine's got the highest atomic mass. So I use this problem to illustrate that number 4 doesn't have to be hydrogen, it can be whatever it is. In this case, number 4 is going to be the methyl group. Okay, so because you went to carbon, 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 and then this carbon went to 3 hydrogens, and this carbon is attached to 2 hydrogens and another carbon, right? There's a hydrogen, hydrogen, and that carbon. And then what is this carbon attached to? Well, it's attached to hydrogen, and then you treat the double bond like 2 single bonds, so it's attached to carbon, carbon, right? So if we expanded that out, so instead of that carbon being, so we take the double bond and make it 2 single bonds. So that carbon's attached to 2 carbons and a hydrogen. And so formally and then this next one, you would do the same too. So if we just kept working our way around the ring, so you expand the double bond out like that. So this carbon is attached to 2 carbons, and then the other carbon, did I do that right? No. There we go. Yeah, that's right, because it's in sequence. Okay, but anyway, it's easy to tell the difference, right? This CH3 goes to 3 hydrogens. This carbon to the left goes to 2 hydrogens and a carbon, and the carbon to the right goes to 2 carbons and a hydrogen. So in terms of order, so CH3 is 4, to the right is number 2, and to the left is number 3. And then if you draw your arrow from 1 to 2 to 3, 1 to 2 to 3 is also counterclockwise, so the stereochemistry here would also be S. Okay, so what do you do if number 4 is not on a wedge? What do you do if it's not on the dashed wedge or the solid wedge? What if number 4 is on the line, like in this example? It's not on the solid wedge, it's not on the dashed wedge, it's on the line. So if you have a molecule drawn like this, then you cannot use this method that we just went through. That method will not work. And this illustrates why. So if we assign priorities, that's 1, that's 4. The ethyl group is 2, and the methyl group is 3. So if we did our arrows 1 to 2 to 3, then you would want to say, okay, that's counterclockwise S. Well, what do you do? Do you keep the arrow the same, or do you flip it? Well, you don't know, because there's not a rule for that. Because it's not on the dash, it's not on the solid. And furthermore, if we did the same to this molecule, that would be 1, 2, 3. Well, now the arrow is clockwise. Are these two molecules different? And the answer is no. So for example, what's the difference between these two molecules that I have drawn? So if this is coming toward you, that's chlorine, and this is going away from you, so that's methyl. So between these two molecules, all that I've done is this. So here it looks like the solid wedge is on, that would be, I think, your left. And if it did this, then it looks like the solid wedge is on your right, but that did not change the stereochemistry of this carbon. It's simply drawn from different perspective. And if we call this, so if this is the green, yeah, so that would be number 4. So it's on your right like that. And if I do this, it's still on your right. But it flipped these two, which the blue and the white, which basically changed the direction of the arrow, but it did not change the molecule. So the point is, if number 4 is on the line, you cannot use this method. You have to use a different method. And that method is, we're going to draw, so if number 4 is on the line, then we have to use a Fischer projection to figure out if it's R or S. So Fischer projection, we're just going to, it's kind of like a Newman projection. We're going to take a 3-dimensional structure and we're going to write a 2-dimensional drawing that retains the chiral information. Okay, so how to draw a Fischer projection. So if the wedge points up, then we're going to basically work. So I've got the same molecule drawn twice so that I can show you how to visualize this. So if the wedge is pointing up, then we're going to look down. So you're going to be up on the top of the page looking down. So there's your head. Establish where your feet is. Doesn't matter. You can put your feet this way, or you can put your feet that way. So if you can picture yourself, so if that's the molecule, and if you can picture yourself here, and let's say your feet are over here and you're looking down at this, then so if I was doing that, I would see the blue on my left, and I would see the white, I would see the blue on my left, and I would see the white on my right, and I would, if my feet are down here, then I would see the green towards my feet, and I would see the red towards my head. But if I was over here looking down like this, and my feet were on this side instead, then the green would be towards my head, and the red would be towards my feet. And if I was laying here looking down, then the blue would be towards my right hand, and the white would be towards my left hand. Okay, so if I'm looking at it from this perspective, so the hydrogen is towards my head, and the ethyl group is towards my feet. So if I'm looking down from this perspective, so always looking to the wedge, then the chlorine is on my left hand, and the CH3 is on my right hand. So if I just change my orientation so that my feet pointed towards the other direction, then now the ethyl group is towards my head and the hydrogen is towards my feet. So now if I'm looking down on the molecule like this, so the CH3 is on this side of my iPad, so it's on my right hand now, Is that right? Make sure I did. Yeah. Oh, let me think. Left, right, head, feet. Left is chlorine, right? Oh, these are not the same molecule. That's why. That's why it's confusing me. Yeah, these are different molecules, right? Because I have the chlorine and the methyl group flipped. So these are enantiomers of each other, right? If two things are the same and two things are different, then that's the enantiomer. So these are going to be enantiomers of each other. But yeah, if looking from this perspective, ethyl's on towards my head, hydrogen's towards my feet, and methyl's on my right hand, and chlorine's on my left hand. Okay, so whenever you're drawing a Fischer projection, you must look at the molecule in such a way that vertical bonds project away from you. So if I'm looking down at the molecule, the wedges is coming towards me, and the H and ethyl group are projecting away from me. So that's what this means. So those are projecting away from you, and these are projecting towards. That's confusing. Okay, yeah, so these have to project away from you, the vertical does, and the horizontal have to project towards you. So otherwise it's not a proper Fischer projection and you're going to get the answer wrong. So you have to always visualize the molecule into the wedge, and the wedge then is always my horizontal. So that when I say wedge, I mean the solid and the dashed wedge. So that's always my horizontal, and the lines are always my vertical. Okay, so those are our two Fischer projections, and the chiral carbon. So that chiral carbon is there in the Fischer projection. So what we want to do now is assign priorities 1 through 4, just like before. On the Fischer projection, where did it go? So if we assign priorities, so chlorine is number 1, ethyl is number 2, methyl is 3, and hydrogen is 4. And then if you draw your arrow from 1 to 2 to 3, that's counterclockwise, that would be S. And then chlorine's 1, ethyl's 2, methyl's 3, hydrogen's 4. 1 to 2 to 3 is clockwise, that would be R. So when you're doing Fischer projections, so the rules are you assign your priorities 1 through 4, you draw your arrow from 1 to 2 to 3. If number 4 is in a vertical position, which it is here, so it means it's top or bottom. So in this case it's on top, in this case it's on bottom, but that's vertical. So if it's a vertical, then the arrow remains. Whatever arrow you come up with from 1 to 2 to 3, that is your answer. So here 1 to 2 to 3 was counterclockwise, so it's S. Here 1 to 2 to 3 was clockwise, so it's R. If your number 4 is in a horizontal position, so if number 4, let's draw it here. So if number 4 is here or here, then when you draw your arrow from 1 to 2 to 3, you have to reverse the arrow, and then that is your answer. So we'll work some examples, and hopefully it makes sense. Okay, so let's practice. Let's assign each of these chiral carbons as R or S. So if you're going to, so let's see. So let's assign priorities first of all. So that's number 1. No, it's not. So that carbon's got a chlorine attached, and an oxygen attached, and a carbon and a carbon. And chlorine has the highest mass, and then oxygen. So you might say, well, iodine's got a higher mass than chlorine or oxygen, which is true, but you didn't run into iodine first, you ran into carbon first. And chlorine and oxygen have a higher mass than carbon. So chlorine's 1, oxygen's 2, and then you run into a carbon and a carbon. This goes to 3 hydrogens. This goes to H, and iodine has the higher mass, so this is 3, and this is 4. So 4 is on a line, so we have to use a Fischer projection to solve this. So we're going to stand here and look into the wedge. So now the wedge is pointing towards the right, so I'm going to stand on the molecule's right and look into the wedge from that perspective. So if you do this, the OH is towards your head, the CH3 is towards your feet, and so if you're looking at the molecule, the wedge from this perspective, then this is on your left hand and this is on your right hand if you're looking from this perspective, and that's towards your head and that's towards your feet. So the Cl would be on my left hand and the CH2 iodine's on my right hand. So that would be the way to draw the Fischer projection. If you just wanted to know it's R or S, you just have to get the numbers in place. So that's 1, that's 3, that's 2, that's 4. And then 1 to 2 to 3 is counterclockwise. No, that's clockwise. That would be R. 4 is in a vertical position, so the arrow remains. So this is the R isomer. Okay, so now we have a molecule that looks like this, where the wedge is pointing down. So you need to be on the floor looking up, or on the bottom of the page looking up. So now you're on the bottom looking up, and establish where you want your feet. Does not matter. So you can put your feet wherever you want to put them. So let's just put them this way. And then you're looking up. So you have to keep in mind, so you're laying on your side, looking at the molecule. And so if you're laying on your side looking at the molecule and your feet are down here, so if I'm laying on my side, then that would be my right hand with the coming towards the red, and my left hand would be going towards the green. So let's see. So the methyl is towards my head, the ethyl is towards my feet, and the chlorine would be towards my left hand, and the fluorine would be towards my right hand. Okay, now assign priorities. Chlorine's 1, fluorine's 2, ethyl's 3, methyl's 4. 1 to 2 to 3 is clockwise again. 4 is in a vertical position, so the arrow stays clockwise, so that is R. So if we wanted to name this molecule 1, 2, 3, 4, so that would be, so the stereochemistry always comes in the front in parentheses, so that would be R, 2-chloro, 2-fluoro, butane. Right, so we can name that molecule. We know how to name that. We couldn't name this molecule because we don't know how to name alcohols yet. And we couldn't name this molecule because we don't know how to name thiols yet, but you could figure out R and S. So now the wedge is pointing towards the left of the paper, so we need to stand at the left of the molecule and look to the wedge from this perspective. So if we stand over here and look at the molecule from this perspective, then H is towards your head, CH2, SH is towards your feet, and OH should be on your right hand, because it's coming out of the paper, and methyl's going behind the paper, so it should be on your left hand. Okay, assign priorities. So oxygen's 1, and this is because you don't run into the sulfur yet, right? Sulfur would have a higher mass than oxygen, but you're not comparing oxygen to sulfur, you're comparing oxygen to carbon. So, but then this carbon with the sulfur is going to beat this carbon with the methyl. So that's 1, 2, 3. So another example, 4 is vertical. So, and another example, 1 to 2 to 3 is clockwise. So that's another R. So hopefully one of these is S. Okay, so this one, so the wedge is towards the ceiling. So again, you got to be on the ceiling looking down. So let's put our feet. Oops. Doesn't matter where you put your feet. So let's put it that way. So, and you look down into the wedge. So if you do that, you should see this ethyl towards your head, and that towards your feet. And on my left hand should be the aldehyde, and my right hand should be the hydrogen. Yes, that is right. Okay, assign priorities. Let's see. So hydrogen's going to be 4, and this is definitely going to be 3. And how to decide between the other two? So we go to a carbon and we go to a carbon. That's the same. and then they both have a double bond oxygen, so that's going to be the same, but then this goes to an oxygen and this goes to a hydrogen, so this is going to win. So this is going to be 1 and that's going to be 2. And so 1 to 2 to 3 is clockwise, but 4 is horizontal, so we have to reverse the arrow. So this is going to be S. So it normally initially be R because arrow's clockwise, but 4 is horizontal. So reverse the arrow. But really we didn't have to do all of this work because 4 is on a dashed wedge, so we don't need a Fischer projection, right? We can just do 1, 2, and 3 and draw your arrow from 1 to 2 to 3, which is counterclockwise, and 4 is in the dashed wedge, so the arrow stays counterclockwise. Right? If 4 is on the solid wedge, we would reverse the direction of the arrow. So in this molecule, you would not need the Fischer projection, and I recommend you not use the Fischer projection unless you have to, unless 4 is on the line, because if you go to a Fischer projection, then that just introduces a place where you can make a mistake. Because if you get 2 groups in the wrong spot, you got your answer opposite. Okay, and so 2 more examples. So let's assign the stereochemistry to these 2 carbons. So again, you could pause the video and see if you could figure it out on your own, and then you could check the work. Okay, so if we do this, so let's just assign 1, 2, 3, and 4 first. So chlorine's going to be priority 1. And then we go to a CH2 and a CH2 and a CH2, that's the same. So from this one we go to H, H, and O. From this carbon we go to H, H, and C. And from this one we go to H, H, and C. So this is definitely number 2. And then between, so now we're at this carbon and this carbon because those 2 pathways are the same at this point. So this goes to H, H, and N, and this carbon goes to H, H, and another C. And so this beats that. So this is going to be pathway 3, and this is going to be pathway 4. Okay, so if we wanted to draw, so 4 is on the line, we need a Fischer projection. So if you wanted to, now it's pointing towards the bottom, so you got to lay on the bottom and look up at the molecule. So if we're looking at the molecule like that, so you should see 2 towards your head and 4 towards your feet. And okay, I gotta get my visual here. I should see 1 towards my left hand and 3 towards my right hand. Right. That should be right. So then 1 to 2 to 3 is clockwise, 4 is vertical, so the arrow stays clockwise. That's the R isomer. Okay, how about this last one? Well, so first, so what you have to recognize, first of all, is that is not a chiral carbon, because that pathway is the same as that pathway. And that is not a chiral carbon because that pathway is the same as that pathway, right? You go to CH2, CH2, CH with a BR, either direction that you go. And for the carbon with bromine, you go to CH2 top and bottom, CH2 top and bottom, CH with the chlorine top and bottom, same pathway, not chiral carbons. So there's no R and S there, right? But there is stereochemistry there because you do have cis and trans, right? So this would be cis 1 bromo 4 chloro cyclohexane, but no R and S. And the other molecules we can't name because we haven't looked at how to name those different functional groups, but they do have chiral carbons that you should be able to figure out are they R or the S. So last point here, so whenever I ask you to name molecules, this would be one thing that students forget all the time, is to put R or S or cis or trans in the name of the molecule. So don't forget to do that. Okay, that's all.